Hello friends, I welcome you in lecture number 10 on applications of integration. In this lecture we will discuss another method for finding the volume of solid of revolution. This method is known as washer method. So we will use this washer method if the region we revolve to generate a solid does not border on or cross the axis of rotation, and if we have that type of region, then the solid which will be generated will be having a hole inside it, or we will have a cavity in the middle of the solid. So to understand this method, we first consider this example. The region are enclosed by the curves y equal to x and y equal to x square is rotated about the x-axis. Find the volume of the resulting solid. So first we decide the intersecting points of these two curves, y equal to x and y equal to x square. For that we put y equal to x in this equation. So we have x square equal to x, that is x square minus x equal to 0. Therefore x times x minus 1 equal to 0. Therefore x equal to 0 and 1. And because y and x are equal, when x is 0, y is 0, when x is 1, y is 1. So these two curves will intersect at origin and at this point 1, 1. So first we sketch the region R enclosed by these two curves. So here I have sketched this x-axis and y-axis, and I consider this much distance as 1. So this point is 1, 1, and here we have origin. So we first consider y equal to x, that is this line passing through origin and this point 1, 1, and y equal to x square is the parabola and it is also passing through these two points. So we will not consider whole parabola, we will consider the portion of parabola lying between these two curves. So this is y equal to x square, and we have to rotate the region bounded by these two curves about x-axis. So this is the plane region which we denote by capital R, and we have to rotate the region R about x-axis. Axis of rotation is x-axis. So first we try to imagine that what will be the resulting solid in 3 dimension. So for that, first we consider the mirror image of this line. This is the line y equal to x. This point is 1, 1. So mirror image will be below x-axis and it may look like this. So this is the mirror image of this line y equal to x about x-axis. This is the curve y equal to x square. Now y equal to x square, we consider now y equal to x square and its mirror image about x-axis. So its mirror image may look like this. Let me sketch properly. This is the mirror image of y equal to x square, and now we have the solid generated by revolving this plane region about x-axis. The solid may look like this. So now if we consider the cross section of this solid perpendicular to x-axis, then we will obtain this type of disc. Cross section perpendicular to x-axis may look like this. If you cut this solid perpendicular to x-axis, then the cross section will be a hollow disc, that we can understand. For this we have, if we consider this one, then for y equal to x square we will have this disc, and for y equal to x we have this disk, a disk which is denoted by green color. So here the solid will be having a hole inside it. Our solid will be this portion, which we can understand in this way. Our solid will not contain the part between these two. The inside portion, this portion is a hole or cavity. So whenever we have plane region which is the area between two curves, we will have a hole inside this solid, or our solid generated will be having a hole inside it. And if we take the cross section perpendicular to the axis of rotation, then we will obtain a washer, that is area between two circles, like this. If we visualize in 3-dimensional, then we will have this type of washer, that is area between two circles. The cross section of this type of solid will look like this, that we can visualize here. This is inner circle which is denoted by a red line, and this is outer circle. So now to find out the volume of this solid, first we consider its cross section perpendicular to its axis of rotation, that is a washer or annular ring. So first we consider the area of this washer, and we can see area of this washer, which is the portion between two circles, is equal to area of outer circle minus area of inner circle. Now the radius of outer circle is this one. If we consider here, then this distance is the radius of outer circle, that is distance between y equal to x and x axis. So that we can visualize here also. If we consider this line, then this distance is the radius of outer circle or outer disk. So that distance is x minus 0, that is x. So we denote the radius of outer circle by capital R, which is x here, and radius of inner circle is the distance between this curve and x axis, that means this curve, this distance between y equal to x square and x axis, and that we call as inner radius, and that is nothing but x square. So now area of this washer will be pi times area of outer circle, that is pi times rx square, because radius of outer circle is capital R, minus pi times small rx square, that is pi times square of outer radius minus square of inner radius. And we decide the limits of integration for x. So we have taken one washer here, which is the cross section perpendicular to axis of rotation, and after that we start by considering different washers like this, and we find out the volume of each washer, and we obtain the volume by taking the integral from x equal to 0 to x equal to 1. So this is another example of cross section of this solid, which is another washer having this type of radius. Outer radius is x, inner radius is x square. So whenever we have to rotate the region bounded by two curves, then whatever solid will be generated, that solid will have a hole inside it, and the cross section of that solid will be a washer, or will be a annular ring or annular disc. So area of that washer is the area between two circles, that is area of outer circle minus area of inner circle, and the volume is given by pi times integral outer radius square minus inner radius square. Integral is with respect to x between given limits of x. So in general we will consider x from a to b. Now suppose you want to decide the outer and inner radius from the graph of the plane region, then you can decide in this way. Suppose we are interested in the outer radius, then outer radius is the distance between the top curve and axis of rotation. Here curve at the top is x, so distance between this curve and x axis is x. So this distance is outer radius, that is capital R, and inner radius is the distance between axis of rotation and curve at the bottom. So that will give you the inner radius, and you can remember this formula. Volume of the solid generated by this type of washers is given by pi times integral a to b outer radius square minus inner radius square. So here x lies between x equal to 0 and 1. We have to go up to x equal to 1 starting from this. So the volume of the solid is having integral volume of solid generated is v equal to pi times limits of integration are from 0 to 1 outer radius square minus inner radius square. Integral is with respect to x. This is equal to pi times integral from 0 to 1. Outer radius is x, so we have x square minus square of x square, or we can write one more step, x square minus x square square. Integral is with respect to x. So this is equal to integral from 0 to 1 x square minus x raised to 4 integral with respect to x. This is equal to pi times x raised to 3 divided by 3 minus x raised to 5 divided by 5. Limits of integral are from 0 to 1. So this is going to be, for x equal to 1 we have 1 by 3 minus 1 by 5. For lower limit it is 0. So it is 5 minus 3 divided by LCM is 15, and we have 2 pi divided by 15. So therefore the volume of the solid generated by rotating the plane region between two curves is 2 pi divided by 15. So this is the idea of washer method. Whenever we have to rotate the plane region between two curves, then the solid which will be generated will be a solid having a hole inside it, or there will be a cavity in the middle. To find out the volume of this type of solid, we are considering the cross section perpendicular to the axis of rotation, and cross section will be a washer, or it will be a region between two discs. So area of that washer can be obtained by considering area of outer disc minus area of inner disc, and we can obtain the outer radius and inner radius in this way. We consider the distance between top curve and axis of rotation as outer radius, and distance between bottom curve and axis of rotation as inner radius. So here Rx is this distance which is x, and small rx is this distance which is x square, and limits of integration are from 0 to 1. So in this way we can obtain the volume of solid generated by this type of regions about given axis of rotation. So this is all about washer method. In upcoming lectures we will discuss some more problems of Wasser method. So I hope you like this.